The universe is expanding. That's one of the few really complicated concepts that can be distilled into one short, understandable sentence. But anything that gets distilled that much is going to be missing a lot of the story. When we say the universe is expanding, we know that it's getting bigger, but not how, where, or why. So let's start with the basics of how we know the universe is expanding in the first place.
I'm sure you have found yourself looking up at the night sky and wondering just how big the universe is. How could you not? It's just so vast, and we are just so tiny. It's almost impossible not to ponder just how vast it really is, how far it reaches, and I wish I could tell you exactly how big the universe is, but we don't really know. I mean, not only do we not know, but the most logical guess you might make based on all of the latest, highest tech observations that we've made turns out to be not even close. And the unknowability of the size of the universe comes from the fact that light takes time to get to us. The sun, for example, is so far away from Earth that it takes light about 8 minutes to get here. So when you look at the sun, which you should never actually do, by the way, you're seeing it the way it looked 8 minutes ago, when the light that's now hitting your eyes left its surface. Then there's Proxima Centauri, our nearest neighbor star. Light from there takes 4.2 years to get here, which is why we say it's 4.2 light years away. So we're always seeing how it looked 4.2 years ago, not what it looks like now. So basically, the farther away you look into space, the farther back in time you're seeing, which is really cool when you think about it. Now, the first light in the universe that we'd be able to see started traveling about 13.8 billion years ago. That's around 300,000 years after the Big Bang. Before that, the universe was so dense that it was basically opaque. There was light, but it couldn't get very far. So we can only see as far as where that first visible light started traveling from. This is the edge of what's called the observable universe. But here's the thing, the universe is almost certainly bigger than the observable universe. Cosmologists think that there's a lot more out there beyond that edge, and if you could somehow see the rest of the universe, it would look pretty much the same as the observable one, with the same kinds of stars and planets and galaxies. It's just so far away that its light hasn't had a chance to reach us yet, even though it's been traveling for billions of years. So we know that there is more of the universe, but again, nobody knows how much more. To get a little closer to understanding what's all out there, let's start with what we do know. How big is the observable universe, at least? From everything we were just talking about, you would think that the observable universe would be basically a sphere that extends 13.8 billion light years from Earth, because the universe is about 13.8 billion years old, so that's how long the first light would have taken to reach us. By this reasoning, from end to end, the sphere would be twice that size, 27.6 billion light years wide. But it's not, because light might have left the edge of the observable universe 13.8 billion years ago, but by now, the spot where it came from is actually much farther away. Okay, so how did that happen? It's because of another endearingly fascinating trait of our universe. It's expanding. And fast. Everything in space is flying away from everything else because space itself is expanding. It's kind of like dots on a balloon. The farther away the dots are from each other, the more the space between them expands as the balloon inflates. So we might be seeing light that's been traveling for 13 billion years, but during that time, its source has moved much farther away from us. Astronomers can figure out how far because light that's traveling toward us through expanding space will be shifted toward the redder end of the spectrum. And that is how we know that even though light left the edge of the observable universe 13.8 billion years ago, that spot is now 46 billion light years from us, which means that the observable universe is twice as big across, 92 billion light years wide. So, all of this has left us able to see only a tiny part of the universe with no real sense of how far it goes. Which is why you will hear all kinds of mind-blowing ideas about what the universe might be like. Maybe it's infinite, maybe it isn't, maybe there are actually lots of universes when we're just living in one version of the infinite variations of history. We simply don't know what's out there, and we probably never will because most of the light out there, beyond the edge of observability, will never reach us. The universe is just expanding too quickly. Past a certain point, everything is moving away from us faster than the speed of light. And for us, light equals information. Without it, we are just left in the dark.
So we set out to determine how big the universe is, and the answer is we don't know. On top of that, we're going to need to add a few years to any estimates we could have made in that video, since it was filmed in 2015. But at least we have an idea of how big the universe is based on its expansion. Now there's the question, where is the universe expanding? Because it's not expanding the same way everywhere. Here's why the universe's expansion isn't uniform.
Although it might not seem obvious when you look at the night sky, we live in a universe that's expanding faster by the instant. Every day, stars fall over the horizon of what we can see, as the space between us stretches faster than their light can reach us. And we can never know what exists past that horizon. So you might imagine, or you might have heard about, a far-off future where space is stretching faster and faster and where all of the stars and galaxies are over that edge. A future where Earth will be left with a dark, empty sky. But luckily for us, or at least for hypothetical future Earthlings, that's not actually the case, because the universe is expanding, but not all of it. We've known the universe is expanding since the 1920s, but we only discovered that the expansion is accelerating in the 1990s thanks to the Hubble Space Telescope. Hubble was the first tool to measure really precise distances to supernovas out near the edge of the observable universe. And it showed us that out there, ancient galaxies and the supernovas in them are zooming away from us faster than anywhere else. In fact, astronomers realized that they were flying away even faster than expected, which at first didn't make sense. At the time, we thought the universe was dominated by gravity, which pulls things together, so seeing everything accelerate apart was weird. It would be kind of like if you kicked a ball uphill and saw it speed up instead of coming back down to you. Because of this, scientists concluded that there had to be something else going on, something pushing these galaxies apart. They came to call that thing dark energy. Decades later, dark energy is still really mysterious, and there's a lot we don't understand about it. One explanation is that it's a property of empty space. This means that space itself, with no stuff in it at all, has dark energy. And that energy pushes space apart, creating new space, which in turn has dark energy, which pushes space apart, creating new space, which in turn has dark energy, which, you get it. If dark energy is a property of space, that also means you can't dilute it. Its density will always be the same no matter how much space expands. Of course, that density is also pretty small. If you borrow Einstein's E equals mc squared trick and express energy as mass, it's equivalent to about 1 grain of sand in a space the size of the entire Earth. But if you average that over the whole universe, which is mostly empty space, there's more dark energy than anything else. So it dominates, and the universe as a whole expands. That's why the most ancient galaxies are also moving away the fastest. It's taken a long time for their light to reach us, so the universe has had more time to stretch. Now, this might all make dark energy seem super strong. After all, it makes up more than 2/3 of all the stuff in the universe, and it's pushing apart entire galaxies. But it's only powerful because there's a lot of it. Within small spaces, especially those full of planets and stars, dark energy is actually pretty weak. Like the gravity between the sun and the Earth, or the Earth and the moon, is more than enough to overpower the repulsive dark energy between them. In fact, most of the universe's mass is concentrated in galaxy clusters, and these pockets of matter are completely immune to dark energy. They're simply not expanding. And I don't mean the expansion is negligible, like how technically your gravity pulls ever so slightly on Earth, but it's not enough to actually notice. I mean that as far as we know, dark energy is truly not stretching our galaxy at all. This is because it's not a force like gravity, so it works a little differently. To understand how, think about pushing on a heavy door. If you push lightly, it won't open. Push a little harder, and it still won't. But if you push hard enough, once you cross a certain threshold of pushing, it will open. That door is gravity, and within a galaxy, there's just not enough dark energy to push it open. In other words, gravity is too strong. So our galaxy will never expand, because if it can't stretch even a little, then it can't create more space. And that means the amount of dark energy inside will never grow. Of course, this isn't something we've been able to directly observe, like by looking at other galaxies. But multiple observations have shown us what dark energy is like, and they all suggest this should be true. Eventually, in the really distant future, fewer and fewer galaxies will be visible from Earth, and in 100 billion years or so, deep space will be almost empty. But if Earth is still around by then, which admittedly is pretty unlikely, we'd still have a beautiful night sky. Even as the universe stretches, the glow of our galaxy will still be overhead, and we'll have stars, constellations, and even a handful of galaxies bound by gravity to ours. All because dark energy just can't get a foothold around here. Of course, this will only last until the heat death of the universe, but that's another story.
So older parts of the universe have been expanding for longer, but might still have the same rate of expansion. And I said might because physics has yet to totally explain the universe's expansion. So here are our best estimates for the universe's rate of expansion.
Since the moment it began, the universe has been expanding. It took humanity a while to figure that out, but over the last century, astronomers have gotten pretty good at calculating how fast it's happening and how that speed has changed over the past 14 billion years. Right now, there are two main methods for measuring this. You can either observe astrophysical objects like stars and supernovas, or you can use the laws of physics to extrapolate from data about the very old universe. Both methods are great, but they also don't quite agree, and according to a new set of measurements to be published in the Astrophysical Journal, that might not be a mistake. The two numbers might actually be different, and to explain that, we'd have to rethink our understanding of physics. Right now, when we say that the universe is expanding, we mostly mean that the void between the galaxies and other large objects is growing. It's a technical thing, but strictly speaking, the universe isn't expanding everywhere. Regardless, one of the tried and true methods of measuring this expansion requires calculating the distances to stars called Cepheid variables. A Cepheid is a star whose brightness changes over very regular periods of time, and the length of that period is directly related to how bright the star is. So as long as scientists can measure how fast these objects change, they can figure out how bright they are up close. Then they can compare that number to how bright the stars look from Earth to determine their distance. Using sets of Cepheids at different distances, along with data about other kinds of objects, you can then figure out how fast the universe is expanding. There are a few other ways to measure this, but Cepheid variables were especially important for this new study. In it, researchers used the Hubble Space Telescope to look at 70 Cepheids in a nearby dwarf galaxy, the Large Magellanic Cloud. It's only about 162,000 light-years away, which is super-duper close on a universal scale. Then, to make sure their brightness measurements were as accurate as possible, the scientists combined their data with results from a few other sources, including an international collaboration called the Araucaria Project. This group calculated the distance to the cloud a different way, by watching the light of binary star systems change as the stars moved around one another. That movement allowed them to figure out stuff like the stars' masses and how big they are, and by combining that with data about how fast those changes happened and what kind of light the stars emitted, the scientists could ultimately work out how far away they are. After looking at this data, the authors of this new paper reported that the universe is expanding at, drumroll please, about 74.03 kilometers per second per megaparsec. In other words, an object a million parsecs away, or roughly 3.3 million light years, is moving away from us at about 74 kilometers per second. An object 2 million parsecs away is moving away at about 148 kilometers per second, and so on and so forth. 74.03 kilometers per second per megaparsec. That's amazing. It's amazingly specific. Now, despite all the work that went into it, that estimate isn't actually groundbreaking at first glance, since it's basically in line with previous measurements. But the key is that this number has far less uncertainty, and that's causing a problem, because that estimate conflicts with other confident measurements about the universe's expansion. Like I mentioned earlier, Cepheid variables aren't the only way we can figure out how the universe is growing. Another method is by studying the cosmic microwave background, or CMB. This is the oldest light in the universe that humanity will ever see. It dates back to when the cosmos was only about 380,000 years old, and studying it is the main objective of the European Space Agency's Planck telescope. By studying temperature fluctuations in this light, scientists have been able to determine how fast the universe was expanding those 13-ish billion years ago. Then they've been able to use that to extrapolate and figure out what the expansion rate should be today. Those extrapolations are all based on, really well-tested laws of physics. So you would think that these results would match up pretty well with what we've observed with instruments like Hubble. Except that they don't. The Planck expansion rate is noticeably lower than what we've gotten using sources like Cepheids. It's only 67.4 kilometers per second per megaparsec. This discrepancy isn't new, but there was always a chance that it was a fluke. Like last year, scientists estimated that there was a 1 in 3,000 chance that something had just gotten messed up. But now, with this updated Hubble data, the chance is 1 in 100,000, which means that while it's not impossible, it's pretty unlikely that these numbers are wrong. In other words, scientists now have to explain why the observed expansion rate is almost 10% faster than what physics predicts it should be. One current hypothesis is that there was yet another incident where mysterious dark energy caused an increase in the universe's expansion rate. Scientists don't really know what dark energy is, but they believe something like this has already happened twice, once for a brief moment after the Big Bang, and again starting a few billion years ago. So maybe there was another incident like that between those 2 points. Another idea is that dark matter interacts differently with regular matter and light than we think. Dark matter is stuff that doesn't interact with light or charged particles, so it's basically invisible. We only know that it's there because of the gravitational effect it has on regular matter and light. But we could be wrong about how strong its influence is on that stuff. If its influence is stronger, it could have countered the universe's expansion early on. Then again, both of these ideas could also be wrong. Maybe there's some exotic particle we haven't discovered yet that's responsible for all of this. Ultimately, this is yet another example of answers in science just spurring more questions. But there are ways scientists could explore this further, including using gravitational waves produced in black hole and neutron star mergers. Those are ripples in space-time that squish, like everything that exists in space-time, including Earth, just the teeny tiny bit as they travel through the cosmos. Since they don't rely on light, measuring those waves would give us a totally new set of data to study the expansion rate. But right now, this field of astronomy is really young, so we can't draw any conclusions. In our day-to-day lives, narrowing down these big-picture cosmological factors doesn't always feel that important. Like, knowing how fast the universe is expanding isn't going to help you write a paper or get through another day at work. But this field is all about discovering and understanding the fundamental rules for how everything works, from Cepheids way out in space to the gravity that keeps you here on the planet. And in a lot of ways, being curious and exploring big questions is a lot of what makes us human.
Since physics can't totally explain everything yet, there are still some unsolved mysteries in the universe. To hear about a few others, you can watch our SciShow space video about 4 of physics' greatest mysteries. Do you know of a mystery we haven't explained yet? You can suggest it in our Patreon inbox. Get started at patreon.com/SciShowSpace.